Unit 5. This is code generation and optimization. So here we will start with the sixth lecture, and here we will discuss about optimization of the basic blocks. In the last lecture we have discussed about the basic blocks, how to identify the basic blocks and how to find the flow graph. So now we will need to discuss that how to optimize the basic blocks. So optimization of basic blocks, it can obtain we can obtain improvement in running of the code by performing the local optimization within the basic blocks by itself. The DAG representation of basic blocks we need to learn for the optimization. So important technique for local optimization begin by the transferring a basic blocks into the directed acyclic graph. The single expression can be represented by a directed acyclic graph. This idea can be extended for collection of expression within one basic blocks. And now we will learn how it can be represented. There is a node in DAG for each of the initial value of the variable appearing in the basic blocks. There is a node n associated with each statement s within the blocks. The children of n are those nodes corresponding to statements that are the last definition prior to s of the operand used by s. The node n is labeled by operator applied at s and also attached to n in the is the list of variables for which it is the last definition within the block. Certain nodes are designated as output nodes. These are the nodes whose variable are live on exit from the block. Now, what is the advantage of DAG? The DAG representation lets us perform several code improving transformation on the code represented by a block. We can eliminate the local common sub expression, that is instruction that is compute a value that is already been computed. We can eliminate the date code from here. We can reorder the statement, and reordering may reduce the time of execution. We can also apply algebraic law to reorder the operands. Now, finding the local common sub-expressions. For the common sub-expression, we will take one example. So let us consider we have a equal to b plus c, b equal to a minus d, c equal to b plus d, d equal to a minus d, and here we have this diagram and DAG for a equal to b plus c. So we have here b, here c, the b plus c is here, and then we have a minus d. So here we have a, and here so we have here a minus d. So the value of a minus d is b, and next we have c equal to b plus c. C equal to b plus c, it means that we have here the value b, and we have the value here c. So here we have value b, which is already updated, and we will take the updated b and we will take the c value. So here from here we will take b, and from here we will take c. The b plus c, we are storing the result in c. Next, what the statement is that a d equal to a minus d. So this a minus d is equivalent to this one because we have not updated the value of a or d. So we can write here comma d at this location. So the node corresponding to the fourth statement d equal to a minus d has operator minus, and the node will attach variable a and d0 as a children. Since operator and children are the same for the as those for the node corresponding to statement 2, we do not create this node because b equal to a minus d and d equal to a minus d. So we do not need to create here because we have already created here. So b and d is same here. But we can just minimize it, and for the minimization, the block, this you can see this block will now modified by this one. So here we have a equal to b plus c, d equal to a minus d, and c equal to d plus c we have here because d is already created here, and here both b and d are live on exit. So we can take the value of b, we can take the value of d, both the values here. Now we will take one example. So for the common sub expression, thus in this example we have taken this value a equal to b plus c, b equal to b minus d, c equal to c plus d, equal to b plus c. So what we can do, if we have here b plus c, so this b plus c is equivalent to b minus d plus c plus d. So we have already here b minus d, we have here already c plus d, and now we can perform here b plus c. For b plus c we do not need to perform another value, and we can take value from here also itself. So here you can see, here we have directed a cyclic graph in this form. So here we have b plus c, and here we have b minus d, and here we have c plus d, and then this updated value is stored in e here. So this is the equivalence, algebraic equivalence form. Now next we can talk about the dead code elimination. For the optimization, we can delete the DAG. So we delete from a DAG any root that has no live variables attached. Repeated application of this transformation will remove all the node from the DAG that corresponds to the dead node. So here we will take one example. We will take this diagram, a figure 8.13. A and B are live, but C and E are not live here. So we can immediately remove the root labeled E. So this E can be removed here, and when we remove this root labeled E, then the node C becomes a root and can be removed. So the root labeled A and B remains since they each have the live variables attached. So here we have this diagram. And next we can use also the algebraic identity. The algebraic identity represents the another important class of optimization on the basic blocks. So x plus 0 can be written as simply x, or 0 plus x can also be written as simply x, and x into 1. So in diagram what we can do, we can do all this. X divided by 1 is also x, x minus 1, x minus 0 is also written as x. So to eliminate in the basic, so from the basic blocks we can find all these identities, and we can use the value direct x, and so that we can prevent by adding multiplication or division and so on. So this is also another type of algebraic optimization, that is known as the reduction of the strength. So in place of x square, what we can do, we can write like x into x. For 2 into x we can write x plus x, because plus is cheaper than 2 in multiplication. X divided by 2, we can write here x multiplied by 0.5, because multiplication is more cheaper than division. Next we have constant folding. In case of constant folding, we here we evaluate the constant expression at the compile time and replace the constant expression by that value. Since we can use 2 into 3.14, and 2 into 3.14 can be replaced by 6.28. If it is used at 100 places, 2 into 3.14, in place of this we can take direct the value 6.2.